All right, so let's run through some more examples. I wanted to do this molecule, CH2F2. So we're going to calculate, so again, is this polar? We're going to calculate the Lewis structure. We need to know the number of valence electrons. To do that, 4 for carbon, 1 each for the 2 hydrogens, 7 each for the 2 fluorines. That's 20 valence electrons. The shape or the Lewis structure of that is therefore going to look like this, where you have the duet satisfied for hydrogen, you have an octet 2, 4, 6, 8 satisfied for carbon, and you have octets for the fluorines 2, 4, 6, 8. That's going to get you 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 20 valence electrons. Okay. So again, just like for carbon tetrachloride in the last video, steric number is going to be 4. The steric geometry is therefore going to be tetrahedral. And the molecular geometry, since there's no lone pairs, is always, if there's no lone pairs on the central atom, it's going to be the same as the steric geometry. So it's also going to be tetrahedral. Now we have to calculate, do we have polar bonds? So we're going to look at the electronegativities. So electronegativities, where do we get these numbers? We just look at a table that's going to be given to you on the exam, right? So for carbon, the electronegativity is 2.6. For hydrogen, it's 2.1. And for fluorine, it's 4.0. So for the carbon-hydrogen bond, we're going to have 2.6 minus 2.1. That's going to get you, that's going to get you 0.5. And actually, I think the numbers that I'm using, the electronegativity values, let's actually, just for simplicity, in some charts, they'll call it 2.5. Okay, this will just make the example slightly simpler. So we're going to call it 2.5. It was 2.55 on my chart. But anyway, I was rounding up, so let's round down. On your chart, it's going to be 2.5. Depending on how they measure, the electronegativity values can differ a little bit. So anyway, if we do that, that's going to be 2.5 for carbon and 2.1 for hydrogen. That's going to get you 0.4. Okay, so we said, less than equal to 0.4, that's going to be non-polar. Okay, so that's basically a non-polar covalent bond. Okay, so there's no dipole on the carbon hydrogens here. Basically, it's close. It's going to be very weak if there's something there, but we would call it no using this 2.5 number. Okay, what about the carbon fluorine? Okay, well, fluorine is the most electronegative element there is. So it's going to be 4.0 minus 2.5. Okay, and that's going to get you, what is that? 1.5. That is definitely, so that is in between 0.4. Okay, delta electronegativity is in between 0.4 and 0.2, 2.0. So that's going to be polar covalent. Okay, that's definitely going to have a dipole. So pointing towards the fluorine, the more electronegative element. So it's going to look like this, right? And so what that tells you is, hey, we have electronegativity pointing to the right on this molecule, but not on the left. And so net, right, you're going to have a dipole. Those are going to add up to go to the right, right? One's going to the right in back. One is going right in front. Net, they're going to go just to the right. And so you're indeed going to have a polar molecule. Okay? And so the answer is yes. All right. So let's do another example. Tellurium tetrachloride. Is it polar or not? Well, we have 6 valence electrons, 7 each for the chlorines. That's going to get us 34 valence electrons. We're going to have to put our tellurium in the center atom. That's a less electronegative atom. And let's satisfy the octet rule. Okay, it's looking very similar to carbon tetrachloride, except we only have 32 electrons on the board, 8 for each chlorine, right? 2, 4, 6, 8. Octet rule satisfied for tellurium, but we have 2 more electrons we need, and we're forced to put them on the central atom here. Expanded octet. What is that going to do? That's going to give us a steric number now of 5, right? Because we have 4 binding sites, 1, 2, 3, 4, and a lone pair. That brings us up to 5. That means our steric geometry for steric number 5 is going to be based on the trigonal bipyramid. So it's going to be trigonal bipyramidal. Okay. And our molecular geometry, well, it's a trigonal bipyramid with one of the pairs removed. That's called seesaw. Okay. And so how does that look like? Well, it looks like something like this. And I'm just going to have the dash. The wedge one I'm going to remove. That's where the lone pair was. So I'm just going to put it there. But that would be wedge, but we don't really think about that because there's not an atom there. Okay. And so you're going to have chlorine there. And then you're going to have chlorines there. And so now we have to figure out, do we have a dipole? Okay. And so for that, we're going to look at the electronegativities, chlorine electronegativity and tellurium electronegativity. The chlorine electronegativity, look this up on a chart, is 3.2. And tellurium electronegativity is 2.1. So your difference in dipole there is 1.1. That's your delta En, delta change in a difference in electronegativity. Okay, that is in between 0.4 and 2. So that's polar covalent. So at this point, we know that the chlorine's more electronegative, and so we're going to have electron density on all these. Okay, pointing towards the chlorine. Now, is there a net dipole? If we had a site here, there wouldn't be, because it'd be equal opposite directions. You know, this trigonal bipyramid radiating from the center, we would have no net dipole, right? But if you look at this, you know, there's no dipole here going in this way. So you have some going up, some going down. Those are going to cancel. So I'm just going to, in red here, kind of cancel these up and down, cancel, right? And now you have to the left going to the back, and you have to the right, straight to the right. Okay, so it's left to the back and straight to the right. So net, you're going to kind of have it going, bisecting this. So net, you are going to have a dipole, right? I'll go different color here. And your dipole is going to be kind of going that way. Okay, so is this polar? Yes, it's polar. There is a net dipole. It didn't cancel each other out. One thing you'll notice is, you know, anytime you don't have, anytime you have lone pairs on the central atom, you're likely to get a net dipole if you have polar bonds, because they won't perfectly cancel each other out. If you don't have lone pairs on the central atom, you have a geometry where it's going to equally cancel each other out. You think about an octahedron, a trigonal bipyramid, a tetrahedron, a linear molecule, or trigonal planar. All of those, if they don't have any lone pairs, they're going to cancel each other out, even if there's polar bonds. Okay, so hopefully that's a little trick that can help you.